Okay, hello. I am Lynn Silao. I am a consultant and the head of the Institute of Human Genetics, National Institutes of Health, Philippines. And I am a faculty member of the Department of Pediatrics at the University of the Philippines, Philippine General Hospital. You could say that parenting actually starts at the time of conception when a unique set of DNA coming from both parents is actually born. But then this is not all we are, because how our parents took care of us and how our parents fed us from infancy all contribute to our identities. Now, the first 1,000 days of life starts from the period of conception until 2 years of age. It is a crucial time. Why? Because environmental factors such as nutrition builds a foundation for a child's ability to grow, learn, and thrive. Now, babies in the womb get their nutrition from their mothers. These, together with breast milk and the table foods that were all eaten, all contribute to the child's development. And then, needless to say, the effects of good nutrition early in life can reach far into the future. Why? Because good nutrition will now allow the child to overcome childhood diseases. It will now lead to better school performance. And when the child becomes an adult, there will be better paying jobs and also healthier families. So therefore, the mother's diet during pregnancy and the food that was taken from infancy all contribute to crucial factors that we may carry on until adulthood. And these may now spell either health or disease. And this is when nutrigenomics and epigenetics enters the picture. So nutritional genomics or nutrigenomics is a field that has gained so much popularity in the past few years. It investigates how our genetic makeup interacts with our diet. It helps determine which food component is beneficial to the individual's health. It provides an understanding of how nutrition affects the balance between health and disease by altering the expression of the individual's genetic makeup. Let me now introduce the DNA. Our body is made up of thousands and thousands of cells, and in the nuclei of these cells are what we call our chromosomes, which are the inherited material that we get from our ancestors. So these chromosomes, I always liken to a spool of thread, which when you unwind and cut a piece, that is one gene. Cut another piece, that's another gene. And when you study these genes in further detail, these are made up of your DNA double helix, which was made famous by Watson and Crick. These DNAs are made up of your sugar phosphate backbones and sequences of nucleotides, namely your cytosine, guanine, adenine, and your thymine, or your ACGTs. The genetic code carried by two unrelated individuals is actually 99.9% identical, and the 0.1% difference spells the inter-individual explanations to disease risk. And this explains the varied responses of individuals to certain food nutrients. This 0.1% are actually due to your polymorphisms. So polymorphisms are normally present in 1 in 1,200 individuals or 1 in 1,500 individuals. And this explains the differences between people. So if you're talking only about one nucleotide change in a polymorphism, these are referred to as single nucleotide polymorphisms or SNPs. These are the most common forms of variations in which the change is just one nucleotide or one unit of the DNA. It can result to alterations in gene-food interactions by modifying a way a protein encoded by the SNP-containing gene interacts with the food metabolite. Now, when an individual is exposed to a nutrient, it can now lead to health or explain a performance response. Now, the unique response of an individual to a particular SNP will depend on the genotype that that person has. So when the person actually has genotype 1 or one particular genotype and is exposed to one nutrient, it can mean an improvement in response. If, let's say, another person has another genotype and is exposed to the same nutrient, there can be no effect at all. And if another person has another genotype or another SNP and is exposed to the same nutrient, that person may have an impaired performance later in life. So therefore, nutrition influences gene expression, and each individual has a different response to the same nutritional component, and each unique genetic makeup of an individual can influence the balance between disease and health. Now, how do nutrients and genes interact? They can interact directly, wherein nutrients interact with the receptor and behave as transcription factors, which bind at the DNA level. You can have genetic variations, wherein SNPs alters the expression of genes, and this was explained earlier on. You can have epigenetic interactions, wherein nutrients modify your DNA structure and alters your gene expression. Now, the question would be, what is epigenetics? Epigenetics is the study of heritable and often reversible modifications to genes without altering the nucleotide sequence of the DNA. So there are three very important components here. It is heritable. Second, it is reversible. And third would be that there would be no nucleotide changes to the DNA. So how does epigenetics work? There are three genetic machineries involved, namely DNA methylation, wherein a methyl group attaches to a portion of the gene and inactivates the gene or silences the gene. Second would be histone modification. And what are histones? Histones are parts of chromatin which make up your chromosomes, and these will act like a spool wherein your DNA can all wind. No? It recognizes the inactive genes, makes them unreadable. They wind them all together, they make them unreadable, and technically they hide these inactive genes. It also recognizes the active genes, unwinds them, and makes them all readable. And the third would be mRNA expression, and all of these three mechanisms will now explain the phenotype of the individual. Next would be, how does these genetic machineries get turned on? And now you have your environmental triggers that turns on all of these machineries. So what are these? You have smoking, exercise, toxins, diet, infection, stress, cold, heat, and also your drugs. When can you prevent chronic disease? You can actually prevent them while you are still in the womb of your mothers. So if both parents have had good nutrition and were exposed to good bioactive food compounds early on, such as intake of dietary polyphenols from fruits and vegetables, this can now turn on your epigenetic modulation, improve the metabolism of the child, and protect the child against metabolic programming, and thereby giving you a healthy adult later on in life and preventing chronic diseases. So what are these chronic diseases? These are lifestyle diseases which are due to poor diets, poor lifestyle habits, and also a bad environment. And according to the WHO, more than 60% of global disease burden is actually secondary to chronic diseases related to obesity. So you have your gallbladder diseases, strokes, hypertension, cardiovascular diseases, cancers, and type 2 diabetes mellitus. Therefore, people are now focused on preventing obesity. Nowadays, there is a global shift in diet towards increased intake of energy-dense foods, high in fats and sugars, but low in vitamins, minerals, and other micronutrients. The trend is towards decreased physical activity due to the increased sedentary nature of many forms of work. Like people tend to just sit around every day in front of their computers. There are changing modes of transportation. People don't like to walk anymore. They don't like to climb up the stairs. And then there is also increasing urbanization. So what are the factors that contribute to this obesity epidemic? You have unhealthy eating. You have a couch potato lifestyle wherein you have decreased levels of physical activity. You have age, wherein the older you are, the slower your metabolic rate will be. You have socioeconomic status, you have family history, and also genetics. So obesity can also be inherited. And studies have already shown that having parents who are obese, especially mothers who are obese, will now increase the risk of obesity in the child. Examples of chronic diseases would be type 2 diabetes mellitus, which is characterized by an inadequate response to progressive insulin resistance that accompanies age, inactivity, and also weight gain. It accounts for substantial morbidity and mortality from adverse effects on cardiovascular risk and also disease-specific complications such as blindness and also renal failure. Another example would be cardiovascular disease, which is characterized by the formation of intimal lesions due to lipid deposition, inflammatory response, fibrosis, and cell death in blood vessels, and these are responsible for 17.5 million deaths in 2012, representing 31% of all global deaths. Here, nutrition plays an important role in the management and prevention of cardiovascular disease. So what are the molecular mechanisms involved when individual has food intake, and how are these now related to cardiovascular risk? So when an individual actually has intakes food, the gut microbiota comes into play because this will now affect intestinal absorption of the food. You have SNPs, ligands, for transcription factors that will now also affect your gene expressions. You have methylation and epigenetic modifications, and also the effects of lipids, metabolites, and proteins that will now eventually affect your cardiovascular risk. So what is nutrigenomics? This is the study of how different foods interact with particular genes to increase the risk of diseases such as type 2 diabetes, obesity, heart disease, and also some cancers. It addresses how diet influences gene transcription, protein expression, and also metabolism. It views food as capable of reversing disease and stalling aging because it also now allows the development of personalized diet, wherein diets are now specifically designed for a particular individual based on his genetic makeup. It identifies molecular biomarkers and identifies new bioactive food ingredients. It validates the effectiveness of these bioactive ingredients as functional food components, and the long-term goal of all of these would be personalized nutrition for the maintenance of individual health and the prevention of disease. So nutritional genomics is actually based on the following considerations. Diet and dietary components can alter the risk of disease development. Food components can act on the human genome to alter the expression of genes and gene products. Diet can potentially compensate or accentuate the effects of genetic polymorphisms, and the consequences of a diet are dependent on the balance of health and disease state and on an individual's genetic background. Here, when an individual is actually exposed to a particular food component, genetics, epigenetics, and the environment all come into play. And all of these omics technologies are studying all of these biomarkers, how they are exposed, the individual is exposed to these biomarkers, the effects, and how are these related now to health and disease. Why? Because the endpoint that they all want would be optimal health. Okay, several factors such as genes and diet, metabolic profile, environmental changes, and their interaction all play crucial roles in disease progression. And here, this slide actually just shows the different interactions of these genes and exposure to this nutrient. So if an individual actually has intake of grapes or dark chocolates, they may be exposed to your epigallocatechins or your EGCG, and they may now activate certain genes and decrease the expression of other genes also. And the function would be to increase the viability of your beta islets and secretion of insulin, and also enhance beta cell morphology and insulin secretion. Also, if there is intake of vitamin D and biotin, certain genes may be decreased, their activities may be decreased, and certain activities of genes may also be enhanced, thereby decreasing insulitis and increasing insulin secretion and islet function. Intake of fats such as riboflavin and palmitate eventually will decrease insulin secretion, decrease blood glucose, protect an individual from type 2 diabetes. This slide shows the different actions of nutrients to certain genes. So intake of PUFAs, your omega-3 fatty acids, intake of isoflavones activate these genes that are listed here, and eventually excrete fats, regulates inflammatory cytokines, proliferation, there will be proliferation of your PPAR, and eventually reduce atherosclerosis, thereby improving cardiovascular risk. So what are the potential benefits of all of these things? There would be increased focus on a healthy diet and lifestyle. It will motivate the person to a positive behavior change. It will increase the awareness of an individual to risk of certain diseases. It will eventually improve the health and the quality of life of the individual. There would be more focus on the prevention of these diseases and decreased morbidity and premature mortality. Eventually, there would be reduced healthcare costs, and it will allow identification of subgroups of individuals who might be responsive or resistant to environmental dietary interventions. And eventually, of course, you would have better understanding of all of these genetic mechanisms involved in disease susceptibility. Now, in conclusion, nutrition plays an important role in the growth of a child with long-term outcomes for health. In crucial life stages, such as the first 1,000 days of life, wherein there are rapid changes occurring, epigenetic changes induced by the environment can influence gene expression, and these can permanently affect an individual's development and lead to the development of chronic disease later in life. Future researchers should focus now on the nutritional intervention in the critical period of human development, and also on public health efforts for effective preventive actions. Understanding how genes alter the body's response to nutrition and how nutrition alters the body's response to defective genes can promote health. And as a parting shot, individuals cannot change their genes, but they can eat the right foods and take the right supplements to support all of these genetic variations and promote normal cell function. Thank you.